Now it's time to talk about AC circuits and some of the processes and ways that AC circuits work. So the very first thing to address is that of the RMS value. Okay, and RMS stands for root mean square. Okay, and this is a term that's going to come up over and over again with AC circuits, so it will behoove us to take a moment and understand exactly what this means and where it comes from. Okay, so first things first, consider a simple circuit with a resistor R and a variable voltage source V. Okay, now this is not the only way to make voltage sources as far as their signal is concerned, but it is the simplest and the most common, and that is to let your voltage be a sinusoid. Okay, and so of course in this case V naught would be your amplitude, that is the maximum voltage your source is going to supply, and omega is the angular frequency with which the signal oscillates. Okay, and always before we would use something like this, either of these two symbols for batteries, and this is the symbol for an AC source. And when we say AC source, we mean voltage source. Okay, so this, you could think of this as the outlet from your wall, for example. Okay, would be an AC source. And in fact, the outlet in your wall generally actually is sinusoidal. If you had a function generator, you could make square waves, you could make sawtooth waves. There's a lot of different ways that you can make waves. A lot of different shapes, I should say. But the simplest case is the sine wave. Okay? Now, suppose we connect a voltmeter across the resistor. What will it do? Okay? Well, technically, in truth, the voltage across the resistor also has to be a sinusoid with time, and not only that, it actually has to match the signal from the source. So let's call this V sub R, let's call this V sub S, R for resistor, S for source. And that's from Kirchhoff's loop rule, right? Whatever the voltage across your source is, that has to be the same voltage across the resistor, or else Kirchhoff's loop rule is violated. And we cannot have that, right? So what we can say is that these two have to be coincidental. Okay, for resistors, these absolutely have to be coincidental. So, with that in mind, what we want to do now is understand what this voltmeter is reading. Okay? And if I have an analog voltmeter, what I would see, right, if I had a scale of voltage, this would be 0 volts. Maybe this would be plus 10 volts. This would be minus 10 volts. and I would have a needle that would just kind of go back and forth if the amplitude here were indeed 10 volts, then my needle would just kind of go back and forth at whatever rate the angular frequency was. But that doesn't really help us very much. That's not very illuminating as far as what the circuit is doing. So we need a separate way to think about what's happening in the voltmeter, and for that matter, how to think about the current. Because the current is also going to oscillate back and forth at omega. And if I had an ammeter, it wouldn't really help me out to see the needle just flopping back and forth, 60 times a second if you plug it into the outlet. So with all of that in mind, what we do is we define this RMS value to be the equivalent of a constant DC signal, okay? And the reason we use the root mean square is the following. So suppose I have a voltage signal, and it's a regular sinusoid, so it'll look, something like this, okay? So again, this oscillates between some maximum positive value and an equivalent negative value, right? So what the steps involved here are actually backward. First things first, we square the signal. So this is a sine signal. And so the first step is to square it. And the reason we do that is that puts everything on the positive axis, right? So a squared sine wave. My artwork is not very good, but you get the idea. Okay, and so this puts everything on your positive axis. And then we take the average. Now, how you take an average of a sine function, okay? So what we want to do is we want to take the average of the source squared. Okay, so anytime you put a bar over something in statistics, that typically means the average. So we're going to take the average of the square of the source signal. And the way we do that is this is a time average. Okay, so what that means is if I look at one complete cycle, now one complete cycle on the original sine graph is from here to here. So one complete cycle on the sine squared is from here to here. Okay, so just bear that in mind. And remember that we have this relationship that our period is equal to 2 pi over omega. All right. And so the way you take a time average of a function is to take the integral of that function over one period. Let me actually back up one step here. Okay. And so again, the whole idea of an average is to add everything up. So you're adding all of these little chunks up, which is the definition of an integral, but the other definition is, of course, the area under the curve. So you're going to add up the areas of both of these parts underneath the sine squared curve, right? you're adding all of those up, but then of course the definition of an average is to divide by something. But if this is a time average, then what you're doing is dividing by the period t. So this is the definition of a time average calculation. So in higher courses, they may assume you know what it means to take a time average, and if you've never seen it before, it can be fairly confusing if they don't actually explain what you're doing. So this is what you do to take a time average. Now, your time average does not necessarily have to be of a sine squared. It's just whatever function you're taking the time average of. So the time average of your sine function, well, half of your area is above the t-axis, half of it's below. So the time average, let me draw it this way. The time average of your source would just be 1 over t integral from 0 to t v naught sine omega t dt. Okay, but for a sine function, this is always going to be 0. And these exclamation points are not factorials. They're just to drive home the point that that is a 0. Okay. But for this function, this turns into v naught squared over t integral from 0 to t of sine squared omega t dt. Okay? And if you know anything about how trigonometry relates to calculus, then this integral is immediately easy to evaluate, because cosine squared plus sine squared equals 1, and they both contribute half. So cosine squared theta plus sine squared theta is equal to 1/2. And so this is equal to 1/2 of t when you actually evaluate your bounds. Okay? So the result is that your time average function of the sine squared becomes v naught squared over 2. Okay? So your time average is this level right here, v naught squared over 2. Okay? So that represents the average of your square of your voltage signal. Okay? This v naught squared over 2. And then the last step in the process is to take the square root. Okay? So VRMS is equal to the square root of the time average of your square of your voltage signal. Okay? And so the time average of the square of our voltage signal was v naught squared over 2. So this is the square root hang on, oh, there we go. V naught squared over 2, v naught over root 2, or very approximately 0.707 v naught. For most calculations, 0.07 or 0.707 is all you will need. Okay, very, very seldom, at least in this course, will you need more precision than that when it comes to the square root of 2. So what this means is this represents the constant value used to evaluate properties of AC circuits. So if we come back to this simple circuit with the AC source and with the resistor, okay, then what we would say is that the RMS current is equal to our RMS voltage divided by the resistance. Okay, and so pretty much everything follows from this. Everything in our AC circuits follows from this. Okay, so this is how you calculate RMS values. And by the way, VRMS is 0.707 V naught over R, or the same thing as 1 over square root 2. So IRMS is equal to V naught over R divided by the square root of 2, or 0.707, and this is your maximum current. So in this particular circuit, V naught over R is your maximum. Of your current in either direction. Okay, so your source just completely flips at a constant rate in this simplistic model. And for most AC sources, that's true. Even if your signal is not a pure sinusoid, for nearly most applications, your angular frequency will be constant. So the rate at which your current is changing will be constant. Now, that's not ubiquitously true, but for a lot of applications it is, and certainly for our applications here. Okay, so recognize that, and that is how you calculate the RMS values, where RMS comes from, and hopefully a little bit about why we use it. Okay, it's not very useful to watch ammeters just completely bounce back and forth. So we want a way to measure things about the circuit that we can take to be constant, even if the actual signal and current in the circuit aren't constant. Okay, so this just gives us a way to build analogs to do the math with Kirchhoff's rules and with Ohm's law with AC circuits that would be untenable otherwise if we were trying to evaluate the current and voltage across elements at every single point, given that that those elements are changing, since the sinusoidal is time dependent. Okay, so there is your RMS, and we will talk about capacitors and inductors in the next lecture.